Hi everybody. We're going to go through this lecture on the physical and mechanical properties of dental materials because there's a lot of information to cover here, and we want to get through it as quickly as we possibly can, as it lays the foundation for most of what we're going to do for the rest of this semester. So it's kind of important that you not only get the terminology and the definitions down, but that you understand how materials react on their own and how those materials will react once they are exposed to the oral environment. So I think that your PowerPoint says name and describe the 4 properties of dental materials, but I believe that should be changed to 3 properties of dental materials. Explain how physical properties of dental materials affects the performance of the material. Compare the thermal conductivity of dental materials and tooth tissues, and explain the significance of those differences. Very important in the oral cavity. Identify the significance of the coefficient of thermal expansion in the oral cavity. It has significant implications in the oral cavity. Describe percolation and how it relates to choosing a dental material. Explain the property of galvanic shock and identify when this property can be seen in the oral cavity. You would be surprised that you could potentially find this occurring in a patient's mouth. Distinguish between a high and a low contact angle and the implications it has for dental materials. Explain the Knoop hardness number and how it affects dental materials, and interpret a modulus of elasticity number. So when we look at the property of dental materials, there are at least 3 properties that we will that you should be aware of, but we're only going to cover the physical ones. So these are all of the properties that are going to talk about the mass of the material, the energy, the force, etc. And a little subgroup of that are the mechanical properties. So these are things like, you know, how well does the material resist forces placed on it? And a lot of the mechanical properties are dependent upon how much material is present, the size of the material, the shape of the material, etc. So chemical properties and biologic properties are something that we really won't get into that much. We will talk about setting reactions, like being exothermic, and we will also, and that comes into play really when we're talking about mixing some of the things that we'll work with this semester. The biologic properties, mostly what we're looking at there is just the fact that anything that we place in the oral cavity has to obviously be compatible with the oral cavity. And for many reasons, there are materials that are not biocompatible for every person, things like allergies to the ingredients, as well as, you know, properties of heat and light and things like that, that we just can't work with, you know, certain properties, or certain patients can't have certain materials used on them. So these are all the physical properties that we're going to take a look at and that you need to be familiar with, especially when it comes to choosing materials for your patients. There will be lots of times when you choose a product, let's say a desensitizing product, and you use it on your patients and you like it, you're getting great results, but there's this 1 or 2 patients in your practice that when you've used the product on them, they've had some type of a reaction, or the material does not behave in the same way in that patient's mouth as it does in other patients' mouths. And we have to recognize that that product is not going to work, and we have to sort of be a detective and figure out why isn't it working, and how can we change it, how can we make it different, or should we move on to another product that doesn't contain the same properties. So this chapter is very, very important to us as hygienists, although, you know, it probably at first glance doesn't seem like it. So when we're talking about physical properties of a material, we're talking about things like looking at how much does something weigh. There are obviously products in the dental world that are extremely heavy and products that are super, super light. One thing that comes to mind is when we're talking about radiographic equipment, you know, the XCP, the weight of an XCP, the weight of a snap array. In some patients' mouths, it might just be too heavy, and we have to find different ways around that, use different products. Does it melt or does it evaporate? There's one product we have in our clinic here at CCBC that has such an incredible high vaporization rate that when you put this product on your tray, in 15 or 20 minutes, it will have completely evaporated. So that has a lot of significance when we're talking about timing of using materials. If it does melt or it does evaporate, how much heat does it take for that to do that? You know, the heat of the oral cavity cause something to melt. Does it conduct heat? This is a big one. For patients that have, and we will talk about this, that have restorations in their mouth that are made of metal, those are great conductors of heat. So when someone drinks something cold or drinks something hot or eats something hot or cold, that temperature change will travel through that material very quickly, and it causes pain for the patient. How much heat does it hold? There are lots of products that, you know, once you heat them up, it takes a long time to cool them, and vice versa. Will it expand or contract when heat is applied? Significant to know, especially because the oral cavity is a warm environment, so we need to know how these materials are going to react once we place them in the oral cavity. Does the material flow easily, or is it like molasses? You're going to see this when you all are here for Sealant Saturday. You will see the significance of having sealant material that has a viscosity conducive to allowing it to flow into the pits and fissures on the occlusal surfaces of the teeth. If we have sealant material that's very thick and doesn't flow well, it makes it incredibly difficult to get that sealant material into all of the nooks and crannies on the tooth surface. Is the material hard? How resistant is the material to abrasion? Will it stand up to biting forces? Will it stand up to masticatory forces? When we talk about things like night guards, you know, we need a material in the oral cavity that can handle being wet for extended periods of time, can handle the warmth in the oral cavity, and if it can stand up to those two things, it has to meet the even greater test of withstanding masticatory forces. Will the material dissolve in water? Will it dissolve in oral fluids? Will it take on water? When we work with impression materials, you're going to see that we can't leave that material in the oral cavity too long, and we can't leave it sit out too long because of how it reacts with water from the environment, as you know, whether it's outside the mouth or inside the mouth. So some of the physical properties like density and boiling point and melting point, you should be very familiar with at, you know, this point in your education. So I'm not going to spend any time on those. But vapor pressure. There's a product that we use for sensitivity, like I just mentioned, that evaporates extremely quickly. It has a very high vapor pressure. So what I can compare this to is most of the ladies in this class, and maybe some of the men, I don't know, if you've accompanied females to get their nails done. If you ever gone to a nail salon where they're doing acrylic nails, which they've sort of fallen by the wayside, but the methyl methacrylate is the liquid product that gets added to the powder to create the acrylic that is used for creating fake nails. That liquid methyl methacrylate has a very high vapor pressure, which is why it is kept in a sealed bottle. It's kind of like rubbing alcohol. If you left the lid off a bottle of rubbing alcohol, you know that over the course of a few days, that bottle would become empty. Some products have a very high vapor pressure, and some have a very low vapor pressure. If it's high, it evaporates very quickly. If it's low, it takes a little bit longer. Thermal conductivity. Materials that have a high thermal conductivity value are good conductors of heat and cold, meaning they will transfer any amount of heat or cold very quickly. So things like, we're going to talk about composite materials that are used as filling materials and amalgam, which is a metal, used as a filling material, and how each of those compares with thermal conductivity. So enamel and dentin, when you look on this chart, enamel and dentin have very low numbers for thermal conductivity, and that means that they are very poor thermal conductors when compared with things like the gold alloys. Look at how high the number is for the gold alloys in the middle of this chart. Zinc oxide eugenol and zinc phosphate cements are used to replace lost tooth structure. They're used as filling materials. And with respect to thermal conductivity, the reason that we use these cements, we use them as cements, we can also use them as filling materials, but more often times they are used as like a blanket that goes on top of the tooth. We'll look at this more in detail later this semester, but it's a thin blanket, almost like a sheet actually, a sheet that we put on the tooth before we would put the permanent filling material over top of it when we're doing a filling, when a dentist is doing a filling. So that thin sheet or blanket, just know that it's very thin, but it's sort of acting as a blanket. It acts as an insulator. It acts like an insulating base, very deep in a deep cavity preparation that's very close to the pulp. We are using that type of material, zinc oxide eugenol or zinc phosphate-based cements, using them as a blanket deep down into the tooth that's been prepared for a filling. We use them because they are poor thermal conductors of heat. So whatever restorative material gets placed over top of it, if that material conducts heat, the zinc phosphate cement or the zinc oxide eugenol will protect the pulp and therefore protect the patient from experiencing pain from changes in heat and cold in the tooth. And we will look at this more later on. Composite restorations have thermal conductivities that are very comparable to the tooth structure. Notice when you compare composite plastics here, 0.0025, and you look at enamel is 0.0022 and dentin is 0.0015, it's very close to that. And so they usually don't present a problem as being a conductor of heat and cold. So heat capacity. I want you to think of heat capacity. It's the amount of energy that a material can store, thermal energy. So it's the amount of heat that it can store. So if you are familiar with, on Facebook there has been a post that's been circulating about using a terracotta flower pot, saying that you could turn it upside down and you could heat it up and it would provide radiant heat to an entire room. It can provide heat because that clay material in that terracotta pot is a conductor of heat. It stores the heat and it radiates that heat. The heat comes off of that material, but it stores it. If you took the heat source away, if you took the fire away from underneath the terracotta pot, that terracotta pot would stay warm for a very long time. Just like your thermal coffee travel mugs. So some of those are insulated, and the way that they're insulated, they have a material in them that once you put a hot liquid into that cup, it takes on the heat and it keeps the heat inside of it. That is an example of heat capacity. That's thermal energy being stored temporarily in the sides of your travel mug. Heat diffusion. Both heat diffusion and heat of vaporization are high numbers compared to heat capacity. And think about it this way. It takes 80 times more energy to melt a given quantity of ice than it does to increase the temperature of the same amount of water by just 1 degree. Because the high heat diffusion of water allows ice to cool your drink without instantly melting. So think about that. This is why when you put ice cubes into your drink, the ice cubes don't instantaneously dissolve. Now, of course, if you're putting ice cubes into boiling water, that's a different story. But we're talking about room temperature liquid, and you put ice into it. It takes a while for that ice to melt because water has a high heat diffusion. Coefficient of thermal expansion. This is something that we will refer to repeatedly throughout the semester. Materials that are used in the oral cavity for restorations have a different rate of thermal expansion than, amongst themselves. So composite materials have a rate of thermal expansion that's different than the rate of amalgam. That's different than zinc oxide eugenol. So every product that is used in oral cavity has its own rate of thermal expansion. And what the rate of thermal expansion is how quickly a material will expand when it's exposed to heat, and how much heat does it take for that material to expand. So when your oral cavity gets heated by something you eat or drink, the enamel and the dentin, etc., will expand at a different rate than the material that has been placed on the tooth for a restoration. And what happens is you get the enamel expanding and contracting, you get the material filling the tooth expanding and contracting, and they're happening at different rates. And what happens is you tend to get a separation between the margin of the tooth and the restoration. We're going to talk about the names for that and the name of that process and etc. So when we look at the rates of coefficient of thermal expansion, look at the rate of teeth. This number is between 10 and 15, whereas amalgam is between 22 and 28. Composite, 25 to 68, depending on what type is used. Gold, look at how closely the coefficient of thermal expansion mimics the coefficient of thermal expansion of the human tooth. Based on these numbers alone, it should make sense to you that if I had a cavity in a tooth, replacing the lost tooth structure with gold is the ideal choice, because you're going to reduce the amount of expansion differences between the restorative material and the tooth. Look at sealants. Completely way off the chart numbers compared to a human tooth structure. Porcelain, a little lower than a tooth. Porcelain enamel, right there in the center of a tooth. And then look at wax. Wax is such an incredibly high coefficient of thermal expansion. You apply heat to wax and instantaneously goes from a solid to a liquid. So let me back up just a second. If a plastic filling material was used in a tooth and the patient drank something cold, the plastic filling material would contract more so than the tooth. And when that filling material contracts, there's a space that gets created between the filling material and the tooth. Now that space, within milliseconds, will fill up with oral fluids, with saliva, biofilm, etc. When the temperature in the oral cavity returns to normal, the filling material returns to the normal shape and forces that oral fluid out of the space. So this phenomenon of contracting and expanding is what we refer to as percolation. Now, if a patient has, let's say, aluminum, which you would never have aluminum in the oral cavity, but let's just say this, aluminum restoration on tooth number 3, and they have a gold restoration on tooth number 30, when that patient bites down, they experience a little shock. That shock is referred to as galvanic shock. And this is what happens if you've ever had a piece of aluminum foil in your mouth, like you left it on a piece of chocolate you were eating or a piece of gum you were chewing, and you bit down and you got a shock in your mouth. You experience galvanic shock. And the medium in galvanic shock, because there has to be a medium to facilitate that, are the electrolytes that are in your saliva. Corrosion and tarnish are two things that as hygienists we look out for around our amalgam restorations, because they do tend to break down, they do tend to tarnish, become discolored. They will go from a bright, shiny silver to a blackish color. And corrosion creates little pits and rough areas on those amalgams. And if we have a rough tooth surface, we're going to attract plaque. So when we will talk about how corrosion and tarnish sort of dictate allowing us to, as hygienists, to polish those restorations and remove that corrosion and tarnish. That's another service that we can provide to our patients. Viscosity is very temperature dependent. There is a way to measure it, and it's measured in grams per meter per second, also known as poise. And when we will discuss viscosity in two ways: the viscosity of the material as it is outside of the mouth, and then the viscosity of the material as it reacts inside the mouth. And those two things can be very, very different because of the way that heat and moisture can affect viscosity. We will look at using alginate. The viscosity of alginate will change based on the amount of water that you use and based on the temperature of the water that you use. And there are lots of other materials that will have viscosity issues. If a material is old, it will change the viscosity. It may get more liquefied, it may get more solidified. And we have to, as hygienists, be able to recognize when a material has spoiled, because if the material is spoiled, it may not perform the way that an unspoiled material would perform. And that can have serious implications for you and for the patient. So it's very important that we understand the normal viscosity of a material versus a non-normal viscosity. Wetting. Wetting in the contact angle. So let's talk about this for a little bit. I want you to think about when your car has just been given a very good waxing. So you've applied a coat of wax to the vehicle, or maybe you just got a brand new car. What happens when the car gets wet, when it rains or when you go to wash it? The water beads up on the surface. Now, that water on that surface will, or water on any surface I should say, can be reported in terms of a contact with the surface. So if water is trying to get away from a surface, it's not compatible with the surface, it will sit up very high. And when it sits up very high, not much of the water actually touches the surface. When the water is compatible with the surface, the drop of water will lay down and flatten out and try to hug the surface because it likes it. If it doesn't like the surface, it sits up high, it's trying to get away, that's a high contact angle. If it likes the surface, like low, it has a low contact angle. So if something has a high contact angle, we say it has poor wettability because if you look here, this is high contact angle. This is water beating up on a surface. Notice that only this small amount of the water droplet is actually contacting the surface. Compare that over here where we have this wide area that's actually contacting the surface. So this is good wettability, a low contact angle. This is poor wettability. This is water trying to get away, high contact angle. Very important to understand those two concepts as well. Now, when we look at hardness, think of hardness as something, well, first of all, there is a way to measure it. There's a whole, your book recognizes the Brinell and the Knoop hardness number as two ways to measure the hardness of a material. And there are two, each of these ways has a different way of measuring hardness. But I want you to think of hardness in terms of things like acrylic denture teeth. So when we have acrylic denture teeth, we need them to be incredibly hard because they are going to be replacing natural teeth, and they are going to need to chew our food with nearly the same amount of force. However, you should know that when we lose all of our teeth, our biting capacity is about 25% of what it was when we had our teeth. So if you think of, currently with all your teeth, you chew with 100% capacity. We take out all of your teeth, we're going to decrease your capacity to chew by 75%. So imagine only biting down with your current teeth with only using 1/4 of the force that you normally use. That's really difficult to do. In addition to being difficult to do, we have to make sure that these denture teeth are strong enough to withstand that 1/4 force, but not so strong so as they become brittle. So we don't want the teeth to break off. So that's a really delicate balance between being hard enough and being too hard to where the material actually breaks down. So when we talk about abrasion resistance, that's another property that sort of goes along with hardness when we talk about denture teeth. They have to be able to resist the forces of abrasion. So the teeth can't be worn down by the foods that we eat, by the texture of the food that we eat or the force that we place on them. So, abrasion resistance sort of can go hand in hand with hardness. There are some materials that are both soluble and absorb water. And we use machines like spectrophotometers to measure color because what you say is white is someone else might say is off-white. And what that person says is off-white, someone else might say is ivory. And you just go and stand in the Home Depot or the Lowe's and take a look at the different shades of paint, and you'll know exactly what I'm talking about. If you've ever tried to pick a shade of paint and you have a shade in your mind, you can easily be swayed standing in front of all of those color choices because you don't realize how many shades of something there are until you stand in front of those choices. So color can be measured, and let me just back up here for 1 second. For solubility and water absorption, know that those two are opposite characteristics, and know that not all materials that we use are going to take on water, and not all materials we use are going to excrete water. And those properties of our materials have significance, especially when it comes to distortion. Let me back up 1 second here. So when it comes to color, we use a shade guide in dentistry because it's very difficult to just pick a color. And in dentistry, some of our materials have taken on the ability to fluoresce. And it can cause some people to have teeth that glow under black lighting or ultraviolet lighting, which is why if you've ever seen that Friends episode when Ross over-whitens his teeth become fluorescent. I don't think that's really something that can happen with whitening. They were exaggerating it. But if his teeth were filled with a dental material that had a fluorescent property to it, that's exactly what you would see. So if you've ever been somewhere and they have black lighting and someone was talking to you and it looked like something was very bright inside their mouth, they probably have a material in there that has a the ability to fluoresce quality to them. So interaction with x-rays is really important for us to be able to identify a patient's restorations on radiographs. We have to be able to pick out what is composite versus what is, a filling versus what is a crown. So we have to understand how these dental materials will react when they are radiographed. Very important for us to be able to pick that out. So let's take a look at mechanical properties. We're going to take a look at every single one of these properties, and if you recall, mechanical properties are a subset of physical properties. You have to understand that force is the weight or the load that we put on a material, but stress is the force that develops in that loaded object, and there's only so much force you can place on an object before you overstress it, which leads us to a breaking point. And these properties have a lot of significance when it comes to your instruments. And we'll talk about that. The strain of a material is how much of a change in the length of that material occurs when it's been subjected to force. And we will look at this in lab on Friday as well. You will look at stress and strain. And you'll look at elasticity, the ability of a material to change shape and go back to its original shape. You know there are a lot of materials that you use, and I don't want to give anything away before Friday, that once you distort it, it doesn't go back to its original way or its original existence. So when we look at elasticity of a material, if we place a force on the ends of this material, we end up with compression on one side of the material and tension on the other. So to compress something means to make it smaller, to squeeze it. So if you can imagine being on this side of this material, this side is being squeezed, it's being compressed. Whereas this side is being stretched, it has tension placed on it. And at some point, literally an area, a point on this material is going to withstand the most compression and tensive forces, and there will be some type of breakage that will occur. So when we look at the different types of stress we can place on an object, we can compress it, we can put tension on it, we can shear it, we can put torsion stress on it, which is basically twisting, and then we can bend an object. These are all different types of stress that are placed on our objects. And we can measure stress. Pounds per square inch of stress is equal to the load or force divided by the area that it's covered. And when we talk about mechanical properties, we're talking about the force or the load that's applied to an object. When you exert force on an object, that object develops stress to resist that force. It's pushing back on that force. But the stress works both ways. There's an external force being applied, such as the force of teeth coming together to bite, and there's an internal stress, which is the tooth is resisting the force from the inside. So here, your book gives you this great analogy of the larger the spring, the greater the amount of stress it is allowed to undergo without changing its shape. So as you graduate from a small spring to a larger spring, notice that we can place more monkeys hanging off of this spring, and we still don't have a change in the spring. But if we went back and placed just one more monkey on each one of these, we should get the same amount of distortion of this material. Even though this guy has 4 monkeys on him and this guy has no monkeys, this, because it's larger, can withstand greater stress. But they all at some point will become distorted given enough stress. So when we look at strain, we can measure stress, we can measure strain. And a strain is a measurement of the change in the length of the material divided by its original length. So like I just said, the larger the object, the greater stress it can take on. The larger the object, the more it must be stretched to have the same strain on a shorter object. So stress is our load on an object, and strain is the change in the length of the object. And they are proportional, and they always occur together. Stress and strain show a proportional relationship. As one increases, so does the other. One doesn't exist without the other. Modulus of elasticity, also called Young's modulus, it's a measure of the stiffness of a material, and it gets expressed as pascals, but the numbers are really large. We're talking about pounds per square inch times 10 to the 6th power. I mean, that's gigapascals. So these are huge, huge numbers. But this is what you have to understand. The stress and strain curve. So when we look at the strain curve, the slope is the modulus of elasticity. The yield point is the proportional limit. This is the point at which once we go past here, we're going to have some type of permanent damage. If we go past here and we go too far, that's it. We have broken the material, and the point at which that material no longer has the qualities of its original self is referred to as the ultimate strength. When we look at strain, and we talk about different materials and their ability to undergo stress and strain, compared to the stress and strain curve over here, you can see something like impression material really low. I mean, this material doesn't need much for it to undergo significant permanent changes. A gold crown can withstand a significant amount of stress and strain before it breaks. Ceramic crown, don't need to put a lot of strain on it, but it can withstand a lot of stress before it actually breaks. So you can see here that a gold crown, much, much, much more difficult to break than impression material or ceramic crown. Impression material, you can break it with your hands. A ceramic crown, you would need, maybe some kind of a tool, maybe a small hammer to break it. But a gold crown, you better bring everything you got, because you are not going to distort it very easily. So elastic deformation, the initial change in the length when the stress is removed. So how deformed, how much back to its normal self does a material go? How deformed is it? Plastic deformation or permanent deformation. This is the point where the line begins to curve. An example of this is when you bend a wire hanger and it won't go back to its original shape. So if you've ever worked with a wire hanger before and tried to twist it and bend it into something else, you know that you can't get it to go back to its original self. Okay, sorry about that. Okay, there is no difference between elastic limit, proportional limit, or yield point. They are only different in the method of measurement, like meters versus liters, for example. So I'm not saying that you measure things in meters or liters. I'm just saying that using those terms so that you'll understand the difference between them. So which one you use is dependent upon what it is that you're measuring. Okay. Ultimate strength, as I said before, is that point at which the material will break, and we have ultimate tensile strength and ultimate compressive strength. So when it's a tensile test, you use the ultimate tensile. When it's a compressive, you use ultimate compressive. Essentially, Poisson's ratio is a measurement of the distortion that occurs in 3 dimensions. Resilience is plotted on the stress-strain curve under the curve up to the yield point. So resilience is that measurement all the way underneath the stress and strain curve up to that yield point. Toughness is pretty self-explanatory. The energy absorbed to the breaking point on that stress-strain curve. So we know how tough something is. So on the stress-strain curve, everything up to this yield point on this side is considered how resilient a material is. Everything from the yield point to the failure is considered how tough it is. Okay, so when you're comparing different materials, you will understand, especially when we start getting into pouring up your models, you will understand how tough or not so tough the gypsum materials are that you're going to work with. One is much tougher than the other. Metals have a high fracture toughness. So when a metal pipe, think about it this way, if a metal pipe has a crack in it, it could take years for that metal pipe to break. Yet, it'll continue to do its job. But what happens when you have a crack in your windshield? That small crack tends to break very quickly. It tends to fan out and get larger and larger and continue to grow. So given how glass reacts to a crack, what would you say about its fracture toughness? You'd say that it has a very low fracture toughness. Let's look at fatigue. Think about your scalers. There's going to come a day when you engage your scaler and the tip of your scaler breaks off subgingivally. That's fatigue. You have repeatedly used the scaler in the oral cavity. You have forced stress onto that tip. You have strained the tip. Then you place it into an ultrasonic cleaner, exposing it to chemicals in there, causing possible corrosion. Then you place it in a hot autoclave, repeatedly exposing it to very high temperatures. All of those forces tend to wear on that metal and eventually will cause it to break. Now, let's look at a change in shape. Some properties are time dependent and are difficult to measure but have an impact on denim materials. Things like creep. Creep is very slow. It's a change in the shape of a material, but it happens over a long period of time. Now, stress relaxation, the best way to describe this is to use an example of elastic. Let's use the elastic in, let's say, a pair of pants. When you first buy the pants, they fit great. The elastic stretches slightly around your waist, not too tight, not too loose. But what happens to that elastic over time? From washing it, drying it, and wearing it, it gets stretched out to the point where it's no longer snug, and then eventually the elastic completely gives out and will no longer even be able to hold your pants up. So this demonstrates that if you stretch something long enough or pull something long enough or expose it long enough to some type of force, eventually it is not the same size as the original. Now, stress concentration, if an object has a crack or a dent or a scratch, the amount of stress around that area will increase around that defect. So let's see, how can I best describe this? So if you put a pinpoint amount of pressure on a material, and then you take that pinpoint of pressure off and go back and place, let's say, a quarter-sized amount of pressure in that same area, the area that had the pinpoint amount of pressure applied to it first is going to be more deformed in that quarter-sized area than any other area around it. So whenever you put enough stress on something in one area, if you go back and continue to place stress anywhere around that area, the original stress area is going to continue to be stressed out, basically is what that means. So, let's take a look at what this means for us as hygienists. Things like fillings and crowns, you want hard materials with a high yield strength and a very high modulus. If a crown had a low modulus, what would happen? What would happen is it would break under mastication forces. Margins that are worn down are probably leaking, and they're leaking more fluid because of the rate of expansion and contraction, which is going to allow more fluid to enter the tooth. It's important to look for wear around those margins of restorations. You want to make sure that they are still keeping the tooth protected and sealed. What about a night guard? You know, what characteristics would you want in a night guard? You want a fairly high modulus, although some night guards are soft on the inside and hard on the outside. If alginate had a high modulus, could we take an impression? Absolutely not. The material would be harder than the teeth and not allow the material to conform to the teeth. We wouldn't be able to take an impression. So you want elastic deformation, but not plastic deformation. When pouring a stone model, it's important to reduce occurrences of voids and defects. A crack or a hole in a stone model could easily allow for that material to be broken very, very quickly. So, in summary, dental materials possess physical, mechanical, chemical, and biological properties. The properties of a material affect their performance and dictate how they're used. The stress and strain curve is a measure of the resilience of a material when it's placed under stress. And materials interact with X-rays and will appear on a radiograph, and we need to understand what is material and what is tooth. Galvanic shock occurs when two dissimilar materials touch with a medium, and that medium are the electrolytes found in saliva. The coefficient of thermal expansion affects the margin of restorations as well as tooth structure. So, I hope that you all understand a little bit more about the properties of dental materials, and that if you have any questions, you will certainly ask, and I will see you in lab on Friday.